All right, everyone, let's go ahead and get started. Thank you for joining RJ Lee Group today. I hope everyone out there is staying healthy. Our webinar today is Fly Ash Hazards, Misconceptions, and Analytical Data, how a top-down scientific approach cleared Class C, Class F, and reclaimed fly ashes from GHS HazCom Classification. Don has given similar presentations to the Society of Mining Engineers Mine Exchange 2020 conference, for the Product Stewardship Society, the American Society of Safety Professionals, and the International Occupational Hygiene Association. Here are a few housekeeping items. You should be hearing me now. In case audio clarity is poor, you have two options. One is through your computer, but if that isn't working, you can also dial in. Just click No Audio on the right of your screen and call in via the phone number sent to you from RJ Lee Group at 1 p.m. Eastern Time today. You are already muted, so don't worry about muting your line. Everyone will be muted through the course of the webinar today, but you can ask questions at any time by using the question function on your GoToWebinar panel, which is probably at the right of your screen. In the question feature, only the moderator will see what is being typed, and I'll get to as many questions for Don as possible at the end of the presentation. Also in that panel on the right, I've attached 3 handouts. You don't need them for the presentation, but they're informational on RJ Lee Group and how specifically we work with the construction materials industry. One is titled Iron Sulfide Minerals and Aggregates for the Construction Industry. The second handout details non-destructive evaluation of concrete with impact echo testing, which is written by our PhD, Eric Giannini. And the third handout is on alkali silica reactions in concrete. Another FYI, I will email everyone the webinar tomorrow afternoon, so you can go back and watch it again or share it with a colleague. Also at the end of the webinar, a survey will pop up. Please take the 30 seconds to rate the webinar on technical content and let us know if you have any ideas on future webinar topics which RJ Lee Group should consider. This survey helps us to be better and deliver better information, so please help us out by answering those 3 questions. So just kind of quick how we work with your industry. In the construction material companies, we do industrial hygiene services. We perform analytical services for OSHA compliance, including respirable crystalline silica, metals, etc. For GHS and regulatory compliance, we do product analysis in support of GHS, HazCom 2012, CalProp 65, and other regulatory requirements. For product validation and quality assessment, we perform analytical services to verify the chemical and physical properties and purity of raw metals. And we work in failure analysis, doing parts failure, wear assessment, things like that. For power companies, we perform industrial hygiene services in support of periodic maintenance to include, but not limited to, metals, asbestos, silica analysis, etc. We do byproduct analysis, fly ash, for example, for waste disposal or reuse. And we do product validation of raw materials, like coal, for instance, to ensure it meets the company's specifications. So now let me introduce our presenter, Don Ewert. Don has experienced a career of practice in occupational health and specializes in developing risk reduction plans and management strategies to minimize exposure to extremely hazardous substances. Accordingly, he's worked extensively as both hygienist and toxicologist, performing vivarium studies, preparing GHS compliant documents, and developing numerous international guidance policies affecting sampling methods, engineering controls, and occupational safety. As a frequent presenter on the topic of occupational environmental health and safety, Don is a recognized subject matter expert and participates globally in advanced OEHS training programs, industry events, and professional development meetings. His research findings are published across numerous peer-reviewed journals and available in multimedia format, including books, magazines, and webinars. With this all said, I welcome Don, and I'm excited for the overview he's about to provide on RJ Lee Group's product stewardship services. Don, the floor is all yours.
Thank you, Dennis. Welcome, everyone. Good day. I'm glad you were able to attend and participate in this. Hopefully you'll find it useful. A couple of things. One, I apologize in advance because when I realized as I put this together that with 3 materials, I have a little too much information here to cut it to 30 minutes. So we may run a little bit long, but we will make time for everybody's questions. If you want to stick around, we will do what we can. As with any good program, I certainly don't operate alone. This is far too complicated and sophisticated for one individual to be able to understand it all. The regulations alone are in the thousands and thousands of pages, as well as the regulations applicable to each country. So with me is Dr. Alan Levine, who covers our physics and biochemistry side, as well as chemistry. Dr. Stephen Monaco, who's a chemical engineer, and our senior toxicologist, Dr. Shakil Sagir, with whom I've worked for over 25 years. The company itself has a full host of services that our group offers from a scientific perspective. The few that I will point out is what makes up the XRCM service portfolio that we provide for products. It's computer-controlled microscopy, X-ray diffraction, Raman imaging and spectroscopy, and ICP, either OES or MS. Those are the 4 basic fundamental sciences that we use to characterize products on a daily basis. RJ Lee Group is probably one of the largest electron microscopy firms in the world. At one time, we had 40 microscopes running simultaneously 24 hours a day. That number is now around 15 to 20 with the balance of microscopes in standby mode. But we are a specialist in electron microscopy, which is useful in characterizing materials as well as surfaces, breaks, etc. So enough of all the advertising. Let's get into some meat of this. The globally harmonized system of classification and labeling was brought in the early 2000s by the United Nations as a means of coordinating across the world so that a specific chemical received the same classification as far as hazardous and non-hazardous, but in every country equally. As you can see on the left, Australia harmful, Canada toxic, China non-hazardous, US toxic, EU harmful, and it's just a host of different words that were used. Now it is a common classification, danger, toxic if swallowed. And obviously we're going to talk about the form of the chemical in a minute here. So as a result of all this, in 2013, when OSHA issued the HazCom 2012 notice that by 15 everybody was going to have to comply, it created classification shock. And that classification shock was a realization that a chemical is now more hazardous than once thought, either because of the new classifications that were put into place, or in many cases because the hazards were not evaluated properly the first time. So this continues today, and we see a lot of chemicals out there with a hazard label on them because it's a lot easier to put a hazard label on a product than it is to prove that it's non-hazardous. And for those clients who work with us, they understand that anguish and the time and effort it takes to get to that point. So the problem with that is that when we put a hazard label on everything, we Californianize what we're doing. And like every door you walk in that has a microwave oven that says we're going to give you cancer if you come into our building, we've basically done that with all products. And that really is not a good way for us to go as a society. So we promote classification, characterization wherever possible to try to promote away from just putting a hazard label on out of convenience. And these are the classification cutoffs. This is the concentration level in your product that's going to give it a hazard label. Toxicity is the metals. Skin corrosion irritation is corrosivity. Serious damage to eyes and eye irritation, again, that falls into corrosivity. Respiratory skin sensitization, that's extremely serious. That can result in anaphylactic shock. Mutagenicity, categories 1 and 2, you can see the difference. It goes from 0.1 to 1%. Carcinogenicity, which is the respirable crystalline silica, is 0.1%. Reproductive tox is another one that's very tightly controlled at 0.1%. The operational impact of a hazardous product. What happens? Products with physical and or health hazards increase development costs and require SDS document controls. They are brain damage. You much prefer to have a non-hazardous product. Hazardous product handling necessitates engineering controls and worker protective measures. I always enjoy the part when I talk to a client that has a hazardous product and I ask them, are you using personal protective measures and engineering controls at the dock when you ship that product out? Is the receiving company using engineering controls and personal protective equipment when they receive your product? And the answer is generally no. And if that's the case, why are you writing a safety data sheet that says it's hazardous if you're not following your own rules? Spill response measures must be updated and enhanced. Regulatory requirements expanded across all agencies. You may now have DOT, EPCRA, EPA, Clean Air Act, Clean Water Act, RCRA. Tier 2 reporting levels could be triggered. Products must carry a warning provision in local languages. This is fairly complicated because now you have to adapt the product, particularly in Canada as an example, where you need both English and French. Products must be shipped as hazardous, thus increasing transportation costs, handling fees, time to destination. So you can see the impact is fairly significant. So let's take a look. Let's see what we can do to disprove some of these hazards. Product life cycle. Where does the hazard exist? Is it in the raw ingredients? Is it in the finished product as you presented at the dock? Is it in the anticipated use or extreme upset scenario? Finally, is it in the post-application? Where is that product hazardous? Let's take a look at some examples. This is Johns Manville spray foam, which we all work around, live around in our homes, in our offices, in the buildings, and in the products, and cars, and trucks, and in everything we have. Spray foam is used as an isolator for noise. It's used as an insulant, and it is some nasty stuff. It is the raw ingredients that are nasty. Category 2 skin, Category 2A eye, respiratory sensitizer, again, sensitizer, that's serious. Skin sensitizer, that is serious. Category 1 respiratory, danger, causes skin, may cause allergic skin, causes serious eye, harmful if inhaled. So we know it's harmful in the ingredients. We know it's harmful at the dock. We know it's harmful when it's applied, but is it harmful afterwards? Once it's been applied and cured, would you put it on your child's head and surround your child with it? You're already surrounded with it, so the answer to that question is yes. Meat tenderizer, where's it hazardous? Papain is an irritant. It's also a respiratory sensitizer, extremely hazardous. It also contains tricalcium phosphate, which is a corrosive and an irritant. Is it hazardous? For those that have used it, have you ever had physical problems or presented with some kind of a physical ailment due to it? No. The reason for that is that the raw ingredients are at such a level that they do not cause problems when used. So it's not hazardous at the dock, it's not hazardous in use, and it's not hazardous afterwards. Finally, natural place sand. You can buy this at Lowe's. It's got a silica hazard warning on it. Same thing with traction sand. Yet there's a picture of a child playing in a sandbox and a warning that says we're going to kill your child. So do we play in sandboxes? Do we play on the beach? Right there's the warning. We ignore it, don't we? Just to be fair, Home Depot sells the same product. And on the bottom, you see the Prop 65 warning that says we're going to kill your kid. In the sandbox for the little ones. I won't get into my you can't inhale rocks because I promised my team I wouldn't do that today, but you can't inhale rocks. That's the bottom line. That was the last webinar we did. And if you go online and pull that up, you'll find some interesting stuff on crystalline silica and sand and why it's not classified as hazardous. Top-down approach. HazCom 2012 and Prop 65 bioavailability. With a top-down approach, we are not looking at the raw ingredients going in. We are looking at the finished product and whether or not that finished product is capable of causing harm. That's all that matters to us with the SDS. We don't care how you made it. We don't care what it consists of. All we care about is whether or not the ingredients in there that are potentially hazardous are bioavailable. If they're not bioavailable, it goes away. So let's use crystalline silica as an example. IARC classifies crystalline silica as carcinogenic. And it says that particles with an aerodynamic diameter of less than 3 to 4 microns are respirable. Particles greater than 5 may not reach the alveolar region, which is where the cancer forms. They've also stated that trace impurities affect the biological activity. That's very important. That's very important for all of these things. We call it amalgamation or mineralization, where, in fact, I was working with a product today with a client that contains titanium, but that titanium is not crystalline. That titanium in the product is actually bound, amalgamated into the other mineral species. It's not free titanium dioxide crystalline. So is it hazardous? Absolutely not. National Toxicology Program does not define respirable crystalline silica. OSHA just says that it's respirable, which is a little up to what does that mean. If you look at this chart, you'll see that when OSHA says respirable, their respirable cutoff is 8 microns, when in reality, what's respirable and causes cancer is the 5 microns. This slide got messed up a little in the title here, I see. The IARC has a mean aerodynamic diameter of 1.4 microns with a range of 0.3 to 4, which is the basis for the carcinogenicity. And a more recent article from Particle and Fiber Toxicology identifies an aerodynamic diameter of around 3 microns in adults. So the bottom line here is, even though by convention we use 10 microns, that is not the bioavailable crystalline silica. The bioavailable portion is less than 5 microns. Anything above 5 is irrelevant. It cannot reach your lower alveola and cause problems. Biologically active or not, these are all respirable crystalline silica particles, pure crystalline silica. The ones on the left are finely fractured, freshly fractured. The ones on the right are beach and play sand. You see the difference? The reactive surfaces are much different. The reactivity is much different. The particles themselves have gone to neutral. Hazard classification rules. Very important that we go through this list so you understand when we classify, we're doing it in accordance with OSHA's Appendix A 1910-1200 mandatory, as well as the United Nations, GHS, REACH, CLP, and WMIS. They all use the same rules. Criteria are semi-quantitative or qualitative, and expert judgment is required to interpret the data for classification purposes. The criteria for determining health hazards are test method neutral. They do not specify particular test methods as long as the methods are scientifically validated. Everything that we do here is scientifically validated over and over and over. A chemical need not be classified when it can be shown by conclusive experimental data from scientifically validated test methods that the chemical is not biologically available. There is that biologically available again. Critical. Epidemiological data and experience on the effects of chemicals on humans shall be taken into account in the evaluation. This is very important. If you've got a product that you've worked with for 30 years that is supposedly hazardous, and yet you have no worker, you've got a good medical management program, a good comp program, you track everybody's health, you know everybody's been healthy, and no one has ever reported a problem with that chemical, whether it be a corrosive, a sensitizer, whatever it may be. Our epidemiologist can come in, pull that data, and you can get a non-hazardous classification based on epidemiological data. Conclusive data may demonstrate that the hazard of an ingredient will not be evident, not present a health risk, when present at a level above the specified cutoff. In these cases, the mixture may be classified according to those data. In other words, the cutoffs are a good standard to use, but they are not the definitive answer. Something can be above the cutoff if you have a basis to ascertain that that product is not going to cause harm. And finally, when there is scientific evidence demonstrating that the mechanism or mode of action is not relevant to humans, the chemical should not be classified. In other words, we're not in this game for fish. We're not in this game for animals. We are in this game for humans. So let's jump into some fly ash, see what we did. Class C. To start the characterization, we're going to kick it off with X-ray, and we're going to use that X-ray to determine what the ingredients are using a method called XRD Rietveld. And in the case of one of the Class Cs that we've analyzed, these were the ingredient categories. So what's happened here, and I realize that, that for some this may be confusing. How can you have something that's been combusted and all of a sudden it's got mineral species? That is how this works. With all of the products that we run that have undergone, whether it's slag or it's fly ash or whatever it may be, we find that highly temperature treated products will come back as having mineral species that we can define. For example, quartz, 8%, 71% amorphous. Okay. So this is a good list that we use for safety data sheets to be able to identify what the ingredients are. Okay. And then in that 71 amorphous is the amalgamated blended species that are hard, that are not going to break down, they're not going to salt, they're not going to dissolve. They are minerals, etc., that are bound together in an amalgamation. Just as a comparison, quantitation of crystalline and amorphous silica by XRD bulk analysis is a process of subtraction. This same material shows 11.7% when just analyzed for crystalline silica, with 9% of the crystalline silica amorphous. So it's just a tidbit point. It doesn't really matter. It's all above the 0.1. So with this, we need to get into the respirable fraction and see how much actually respirable crystalline silica there is. To do that, and I've deleted a couple of slides, one of it explains the CCSEM process, another explains the Raman process for brevity, but the bottom line here is we have an interinstrumental analysis approach that we can use where we lay these particles out, we spread them out proportionally across a filter, we coat it, we put it into the SEM, and we now look at the particles and determine what the concentration levels are. We're looking for pure, unadulterated, uncontaminated crystalline silica quartz. So if we're looking for that, we know that's got to be Si rich, silica rich, and oxygen greater than 90%. So we find the particles and we look at the elemental signatures. One is quartz, one is feldspar, one is perlite. This is just an example using a perlite product. We do the same thing with the Raman, and the Raman is unambiguous. It can actually look at the crystalline structure and determine whether or not that particle is specifically quartz, perlite, or feldspar. So the combination of these two analysis methods gives us a very definitive means of quantifying the amount of particulate that is in a certain weight percent and size. So with that data, we start out with our XRD crystalline silica, and we've got the untreated at 8, the treated, which is the less than 45 micron fraction, in this case 11.7. We run that through the SEM, and we then look at how much weight percent there is in a fraction less than 10 and in less than 5 micron fractions, and we get 5 and 1. When we take it over to Raman, however, we find out that it's all amorphous. It's not crystalline. Those same particles were not crystalline silica. They were simply silica rich. A couple of important points here. The IntelliSem reporting limit for silica rich is 0.01%. The Raman reporting for crystalline silica is 0.001. When we hit none detect, we consider it to be non-crystalline silica containing for purposes of Prop 65, either one of those limits. We then advise that it does not need labeling under Prop 65. VFF, as I'm going to describe in a minute, is vacuum filter fractionation. This was not done with that method. Class F, a little bit different in the Rietveld. You can see that it's still about 8% quartz, so we've stayed about the same with the crystalline silica. Calcite, the corrosive agent, less than 1%, and amorphous 76. Quantitation by bulk analysis, 9%. That's basically the same number. Now we're going to take this material, and this was done a few years ago before we introduced the VFF process, which I'll discuss in a second. This used Stokes settling. Stokes settling is an older process. It's been around a long time. It's based on density and liquid particle technology, as well as fluid mechanics and particle settling. And it's got derivations and equations that you use for the settling time in order to separate the less than 10 micron or less than 5 or whatever size fraction you want from the balance of the particulate. It has some weaknesses, which we've overcome with the VFF. Quantity, once we were done getting the 10 micron fraction, we then ran it through the IntelliSem, and you can see here that we got a total in the less than 5 of 0.13. When we back that into the amount of material that was lost, in other words, only 26% of the material is actually less than 10, 73% is greater than 10, we find out that we're at 0.035, which is clearing for GHS purposes. So 0.03 is our final value for the silica rich, which obviously is an ultra conservative approach to the crystalline silicas. We know if we go to Raman, it's going to be even lower than this. So this product is cleared. It did not clear Prop 65 because it didn't meet our threshold for non-detect, but it does clear GHS. Now, fly ash has got some nasty connotations, and it is famously known as potentially killing all the fish in the river, killing all the fish in the pond, and there's reasons for this. When you take fly ash and you dump it in a big pile about 50 to 100 feet deep, and you let it soak and percolate and cook and have all those fun times that it does on the beach party, you're going to get some really nasty stuff. That's waste. What we're doing here is characterizing fly ash as a product, not as a waste. All we want to know is, as a product, if I spill it in a ditch, or if I spill it on the road, or if I spill some into a lake, is it going to kill everything off? I want to know that when workers are exposed to this material, it's fine powdery stuff, when they're exposed to it as they handle it, is it going to cause harm? So the leaching characteristics of fly ash are legitimate. We are not arguing against that. What we are saying is that this is not a waste. This is a product. Much different rules. So we've developed a couple of testing methods to determine whether or not this stuff is indeed going to cause harm. Back when the Class F was done, we were using the RCRA 8 metals to determine whether or not it was harmful, ICP for analysis, and drinking water limits. So we set up a leach using Indiana Neutral, which was designed specifically for fly ashes going back into the mining community. It is a neutral leach method using deionized water, which is to reflect rainwater. And we ran it just in accordance with the method 1311 SW846 for RCRA, and then compared the results against drinking water guidelines. Okay. And in this case, the chrome came up a little high for the WHO guideline, okay, but it did pass the California Title 22 STLC. Okay, so the only thing in this one that was a little questionable is the chrome. There's a couple things going on there. One, this is total chrome. This is not hexavalent chrome, so the amount of hexavalent is going to be significantly less than this number. Basically, from a perspective, we don't feel that this is a significant risk, although the chrome is there. It should be further evaluated, is the bottom line. So what do we do with the environmental stuff? Well, first off, you should be aware that under the HazCom 2012 in the United States of America, we don't care about environmental. We care, but we don't care enough to regulate it because it's an EPA issue. So we don't regulate environmental here in HazCom. And in fact, DuPont decided not to classify environmental hazards, although they'll continue to display environmental testing data in section 12. Okay. So migration protocol to estimate metal exposure. Okay, we've taken care of the environmental. Now, what about the occupational? Well, on occupational, it's a little tougher to figure out how we're going to determine whether or not the metals are going to leach out and this stuff's going to give you the creepy crawlies. So what we did is we found a study that was done for children of jewelry mouthing. And actually, as we've learned since we started doing this, this type of characterization is basically common and used in California for a lot of leachable metals. So this BioLeach protocol basically is soaking the material at body temperature with constant agitation for a certain period of time, and then analyzing the leachate. And it reflects occupational exposure over the course of 30 years. It is not based on lifetime exposure, which is what the Clean Water Act data are based on. It's based on occupational exposure, which is a big difference in years, 70 versus 30. In this case, we're now moved up to the California Title 22 metals, the CAM17, because it's a little more comprehensive, plus it's the most stringent that we can find in the industry right now. Again, ICP, OSHA exposure limits, or ACGIH. We decided to use ACGIH because they are the most restrictive levels for occupational exposures to these metals. And for those metals that actually have an occupational exposure limit, which all of these do, we found that this Class F cleared every one of those limits against the ACGIH. So the way this works is we are envisioning that you would be inhaling, not respirable, but inhaling, dust from this product throughout the course of a day, and that during the day, plus 2 hours afterwards, you would be ingesting this metal through your nose, through your eyes, through your mouth, through your skin, plus 2 hours after work. So we actually, when we ran the numbers out for 0.6 liters of saliva per day ingested, that actually is a 10-hour workday, 5 days a week instead of 8, because we feel that for 2 hours after you get off work, you're probably still ingesting some of the dust. Most of it is blown back out of your nose, or it's spit out, or it's discharged from your skin by washing, etc. But there is a certain amount that we feel is ingested, and we used 0.6 liters of saliva per day to compare against the amount of air that you would breathe in per day of the metal-borne particulate. Okay. Reclaimed fly ash, the last product. Again, with the Rietveld, we see that we now have 10% quartz. So these numbers are all pretty close to each other. Okay. The calcite's at 1%. No standalone XRD bulk analysis. We don't need it. We already know that we've exceeded the GHS. There's no reason to run a separate bulk. So this 10% would be the value that would be utilized for Section 3 reporting. We're going to introduce a new method for fractionation that is much more precise, highly validated. It is called a vacuum filter fractionation method. It's a very meticulous process to collect the naturally occurring particulate very gently, very easy, under occupational health conditions using natural environment, which is phosphate buffered saline. It starts with a 38 micron wet sieve fractionation where we simply bathe the material over and over. Sometimes this can take days to get all of the particles to stop passing through. We continue the 38 wet sieve fractionation, just washing the material down until we do not see any particles by eye under light and white paper coming off. We then stop, collect the less than 38, filtrate, and run it through a 10 micron filter. This is just carefully processed. We start with a very small amount of material, 0.5 grams, so that it coats that filter nice and evenly. That's the starting material before the 38. So by the time we're done, we're down in the micrograms or milligrams. A very small amount of material, so we get nice even layering on the filters, so we don't get compaction. And we collect the 10 micron filtrate. This is the stuff that counts. Now we're going to filter that onto a 0.4 because we don't care about anything below 0.4. If you remember the slide on respirable particulate, IARC told us that anything below 0.4 is irrelevant, and they're absolutely right because that gets into Brownian motion and you actually cannot inhale down to the deep lungs anything below a certain size because it won't move in the air. This is one of the issues with nanotechnology. So we're going to collect that fraction between 0.4 and less than 10. And this is going to be a very small amount of material. In fact, if you look at this slide, you'll see that the weights, we started with 0.5 grams, we got 0.3 grams greater than 38, we got 0.14 grams between 10 and 38, and 0.00165 or 1 milligram, 1.6 milligrams between 0.4 and 10. Our loss on fractionation is 99.67%. In other words, the vast majority of this material is not respirable. Now we're going to run it through our XRD air analysis method, which has a detection limit of 2.5 micrograms per filter. Okay, and you can see that little tiny peaks down there on the bottom. Barely detectable, but functional. Okay, and we're going to see what remember we had 1.06 milligrams. It varies a little bit because we actually have a couple of filters at play here. And weight percentages in total of the VFF fraction was 1.0 weight percent crystalline silica. So we run that back into the 99.70, we are now less than 0.01%, and we have not only passed GHS, we have passed Prop 65, and this product is cleared. There are a couple of important things. XRD air cannot distinguish between free and bioavailable or bound and impure crystalline silica, so we then need to go to the SCCM or to Raman, should it not have cleared. But this obviously cleared very easily, and there is no respirable crystalline silica. For the environmental, we run it through our Indiana neutral leach, and we find out that for all of the metals that were actually detectable in the raw material, we've gone to not analyzing for all 17 metals, only those that show detection, above detection in the raw material, in the as presented material. All of them passed our most stringent criteria, US EPA Clean Water Act MCLs. So it does not leach metals. For occupational, once again, we run it through our BioLeach process and compare it to ACGIH inhalation levels, convert it over to saliva ingestion, and we find out that it has cleared all of those hurdles as well. So we have no crystalline silica in a respirable fraction. We have no metals being leached to the environment. We have no metals being leached to the biohazard. We do not see a problem with this material, and in our opinion, it is clear. So in summary, the Class C occupational exposure was less than 0.001. As you remember, we had Raman data for that. We did not have data for the metals on that product. Class F, 0.03 weight percent. It clears for GHS on the crystalline silica. Occupational exposure was none. It did have a chromium metal of concern that we would want to look at a little bit closer. The reclaimed fly ash, it was obviously non-detect for respirable crystalline silica. There were no metals of concern for occupational or environmental, and that product has cleared. And with that said, I thank you for bearing with me through a lot of material in a short period of time and look forward to any questions you may have.
That's great. Thank you so much, Don. Before we get to the questions for Don, here's a reminder that after the questions are over, a survey is going to pop up. So just give us a few seconds of your time, and that will help us offer better content in the future and let us know how we are doing. So let's see. First question I have for Don, it says, what about pH and corrosivity? Does that make sense?
Yep, that's a good question. So the pH here, the pH limit for GHS is 2 to 10.5. And all of the pHs, we get that out of the Indiana neutral leach at the end of the neutral leach, just like you do with a T-clip. And the pHs were less than the threshold for GHS, within acceptance limits for GHS. The corrosivity, as I mentioned, the amount of corrosive material here is very, very small amount. It doesn't mean that these won't become corrosive in the pit, but because the quantity of corrosive is so low, the buffering capacity is just kind of complicated. And the rules allow buffering capacity consideration. The buffering capacity is very low when you only have 1% of a corrosive agent. So as a result, these are acceptable under pH conditions for products. Now remember, products are different than waste. You can't compare the two. There's different regulations, different rules. Okay.
Don, this says you use the Indiana Neutral Extraction Protocol. What do you think about LEAF, L-E-A-F, SPLP, and TCLP versus that? When would you use one of the other methods, if at all?
Well, I would stay away from anything that's going to be an acidic environment. So one of the things that we do for waste is, and I'm not sure on the LEAF, I apologize, I haven't worked with that for a lot of years, and so I recognize the acronym, but I don't remember what it stands for. But we don't want to do anything that's going to be waste related. And this is one of the reasons that fly ash has the bad reputation, is if we go after this with an acid, we're going to see a lot of metals released. And we don't do that because that's not the intent. This is a product. Our biggest issue is big spills on the road or into a ditch or into a pond or something with a truckload or a train car load of this material that's heading from one place to another. Hopefully I answered that. Sorry.
Okay. As fly ash can change form when exposed to water setup, how do you verify that under VFF you have not agglomerated some pieces?
Well, the question, here's the point. So what we want to know is, we want to know when you're handling this material, is it going to expose you? Is it going to expose the environment? So when you receive it at the dock, if it's agglomerated, does it stay agglomerated? I don't know. But when we go through the VFF and we bathe this for that 38 micron fractionation, and we bathe it and bathe it and bathe it over and over until no particles come visible in the filtrate, we think we've accomplished the de-agglomeration. Remember, it's natural conditions. This is phosphate buffered saline. This is the same thing your body would experience on occupational exposure. This is not using an acid. This is not using a base, an organic solvent. A lot of these methods, including one of the reasons we moved away from Stokes settling and SWRF, is because they use anticoagulants. And if you're going to use an anticoagulant, what good does that do? You're trying to compare an occupational exposure to something that's just been anticoagulated. And it's a chemical on top of it all. So you don't want to be exposed to that chemical. It just doesn't make any sense. We need this to be biologically natural in order to compare against what could potentially occur in the real world. So that's where that comes from.
Okay. Do you have any opinions on CFB fly ash?
I'm sorry, I don't know what CSB is.
CFB? Maybe that's class.
I don't know it. I don't know.
Okay.
I'm not an expert in fly ash. I'm an expert in product stewardship. Sorry, and GHS.
I think that looks like that's all we have here, Don. Let's see, any opinions? Yeah, we got that one.
If anybody wants to follow up with me on those specific questions, I can certainly take a look at that situation, obviously, with that material. I just don't know and not familiar with it all.
And here's Don's contact information.
Yeah. Feel free to call me, write me. I'd be glad to spend a few minutes with you talking about your materials and approaches. We were pleasantly surprised when we did the fly ash and found out that it didn't have any truly hazardous characteristic traits. We were expecting that it would years ago when we first started with fly ashes, and it just hasn't. It's been amazing. And we do have products that come up hazardous. So they don't always fly. Sometimes they do come back. We can't capture everything.
Don, it's circulated fluidized bed waste coal plant.
Okay. Yep. We have not done any of that material. We have not done any of that material. We have done some clinker products out of the bottom of combustion chambers. I didn't include them here, and I'm not familiar with the data now. It was back years ago, but we have looked at some clinker materials, and we have looked at some baghouse materials, but I don't have that data handle in front of me, so just the fly ash stuff.
Well, thank you to everyone for joining us today. Dawn, thank you for your time as well. Everyone stay healthy on this upcoming 4th of July weekend. Thank you for joining us, and please take the survey.